Let me introduce the first invited speaker, who is Tınaz Ekim. She's a professor of mathematics, and her research focuses on structural and algorithmic graph theory and combinatorial optimization. She has several publications on dominating settings graphs, and the title of her talk is Algorithmic Aspect of Defensive Domination Problem. Tınaz, thank you very much for accepting the invitation. We are looking forward to listening you.
Okay, thank you for the introduction and for the invitation. I think it's a very nice workshop. I like focused workshops when it's very fruitful. I hesitate to start right away since we are in advance, 5 minutes. I don't know the custom in Russia, but in Turkey, we usually don't start early and usually late. So I'm just afraid some people might miss the beginning. So what about waiting 5 more minutes and starting in time?
Okay. Tınaz, would you please share your presentation? And
Sure.
yes, we will start 5 minutes later.
Okay, let me. Do you see my presentation?
Yes, yes.
Okay, I just hide this. And yes, I'm sure people will be joining on time and not
Yes,
that
yes.
early. So sorry for this, but
Okay, so we will start after 4 minutes, right?
yes.
Okay.
Okay.
Tınaz, I have a question. You work at Department of Industrial Engineering, yes?
Yes, that's right.
It is interesting.
Yes, you said a mathematician. It's not false. Let me explain maybe a bit.
Okay.
My undergrad is both industrial engineering and mathematics, and I'm mainly in operations research, but more focused on graph theory, problems, and also theoretical parts, not only applications. So yes, I'm in the industrial engineering department working on graph theory.
Very nice.
I guess most of the people are either from mathematics or sometimes computer science.
Yes.
Yeah, but domination problems have lots of applications. So it is also very important for industrial engineers.
Could you please provide some application during your presentation? Yes.
Yes, I mean, I will mention some.
Okay.
Mm-hmm.
Could be interesting.
Yeah, actually, if I knew people were interested in applications, I can talk about a lot of applications of domination problems. Maybe next time, let's say, in some next talk.
Okay. Okay, Tınaz, you can start your talk. We would be happy to listen to you.
Okay, so thank you again for the invitation. So today I'm going to talk about algorithmic aspects of the defensive domination problem. I will start my timing. I think I will try to finish my talk in at most 45 minutes to allow time for questions and comments. First of all, this talk is based on mainly 3 papers. I started to work on defensive domination problem during my sabbatical in the US, together with Arthur Farley here and Andrei Proskowski, who actually are the 2 guys who introduced this problem in a conference paper in 2004. So and since then, nobody have looked at this problem until I went there for my sabbatical. So the first 2 papers with Art Farley and Andrei Proskowski and also Mordo Shalom, the second one, are about polynomial time solvable cases in graph classes. And the last one, which is an ongoing work, is a joint work with my PhD student Bilge Varol and my colleague Kübra Tanınmış. Here we try to propose some exact solution methods. So this work is partially supported by the Horizon Marie Curie staff exchange program cover. And here is the content. I will start with some motivation and problem definitions and talk about the computational complexity. Then mention some hard and easy cases, and then move to the exact solution methods based on integer programming formulations. Well, the motivation. You all know that I think domination problems have some obvious applications in different kinds of resource allocation problems. But this particular one, the defensive domination, allows us to provide stronger, let's say, more powerful tool to ensure security in security networks or for emergency response problems. Well, as I said, this is the first paper where the problem has been introduced. The classical dominating set consists in finding a subset of vertices, D, such that every vertex not in the set has at least a neighbor in the set D. And usually the set D, the vertices in the set D, the dominating set, are seen as guards placed at these locations, which have the ability to protect all its neighbors and itself, right? This is the classical context of domination problems. Well, Here, the question is the following. What if we have k locations which are simultaneously under attack, and each guard still has the ability to protect only one of its neighbors or itself? So here, there's a time component, which and we assume that we can have simultaneous attacks in several locations in the same time. And each guard can be allocated to only one of those locations. It can be either emergency response, answering some, you imagine that you have some equipment, say to extinguish some wildfires, and you have to assign one team to one place because it has the ability to deal with exactly one place at a time. Well, here in the classical dominating set, we assume there's only one attack, right, or one alert. Now, in case of simultaneous attacks, we talk about k attacks. It's a set of k distinct vertices which are under attack simultaneously. And we say that an attack can be countered or defended by a subset of vertices if we can find an assignment of k distinct defenders of this set to the members of the attack A, where either the defender is adjacent to this vertex under attack, or it can also be assigned to itself. So this one. Now, let's take this example. We have A and F, which are defenders. Now, if there's an attack, two attacks, so K is 2 here, at B and E simultaneously, then A can help B and F can help E, and the attack is countered. Okay, the same example here. But now this is not enough to be able to defend only one attack, two attack. We don't know where the two attack will occur, just like in the classical domination problem. It can occur at A and B and E as previously, or any other two vertices. So we will say that a set D is a k defensive dominating set if it can counter every k attack in G. Like previously, an attack at B and E can be countered by A and F. But what if we have a two attack at D and E? Well, F can go to one of them, right? But the other will remain undefended because A is not adjacent to them. So this is not a two defensive dominating set. Whereas if we add one more vertex, D, to this set, then it becomes a two defensive dominating set. And in particular, the attack at DE can be defended by, okay, F goes to E and D defends itself. Okay. So for the notation, gamma K is the minimum size of a K defensive dominating set. And if K is 1, it's the classical dominating set. So we are more interested in higher K values. A few more examples, and please stop me and ask me questions if the definition is not clear. So for this graph, the black vertices form a two defensive dominating set. Well, I hope you see my cursor. If you have we have an attack at this and this vertex, the two leaves here and here, it requires two vertices, two defenders among these three, right? And by symmetry, we have the same in the left side. So we will need at least 4 defenders here to be able to defend any possible two attack. Here, in this graph, the black vertices is not a 3 defensive dominating set because here is an attack which cannot be defended by the black vertices. So this vertex has to be defended by this defender. But then this vertex, this attack has to be defended by that one, no other choice. But the last one here remains undefended, right? Any question up to now?
Well,
okay,
there's
so
some question in chat.
Oh, I don't see the chat.
Oh,
Should
so
I...
the question is like this one. Hello, can we choose one vertex as a defender multiple times?
That's a new version which has been newly introduced, not in the classical defensive dominating set. If we allow multiple guards at the same vertex, this is called the multi-set version, capacitated version, if you want. So that changes the problem a little bit. But it is definitely a nice nice idea. I mean, very useful in practice. Okay, I go on. Well, the complexity of this problem. First, we can see that since we have to defend every possible k attack, and there are n to the k possible k attacks, this is the number of possible k attacks to consider, right? Now, if we fix k, then the instance is just a graph and a positive integer L. And the question, is there a k defensive dominating set of size at most L? But if k is not fixed, then k is part of the instance, and the question is the same. And the complexities of these problems, the two versions, I mean, fixed or not fixed, will not be the same. Let's first see the fixed k defensive domination. Well, if k is fixed, the problem is NP complete easily. First, it is in NP because given a set D of defenders, we can check if D can defend every possible k attack. Well, consider one k attack. Given a set D, we can enumerate all possible defenses, which are nothing but some matchings actually to this set in O of n to the k. And we have in total n to the k possible k attacks. So in overall, O of n to the 2k time, we can check if a given set is k defensive dominating set or not. So if a yes answer is correct or not. And then we can reduce the classical domination to fixed k defensive domination with a reduction which is not very complicated, just by adding a clique here of u vertices and an independent set which is linked to the clique with a matching, so independent edges. And the vertices of this clique are completely adjacent to the whole graph G. Then we can see that there is a dominating set of size at most L in G, if and only if there's a k defensive dominating set in G prime of size L plus k minus 1. So it's not very difficult to see that. And since domination is difficult, we have the NP completeness of fixed k defensive domination. And actually, we know that dominating set is difficult already in split graphs, and this reduction preserves split graphs. So we know that the problem is NP complete already in split graphs. Well, now if k is not fixed, then, well, given a set D, it is co-NP hard to decide if it is a k defensive dominating set or not. So in particular, the problem is not even in NP. Taking the same example, how would you check if a given set D, here A and F, is a dominating set? Well, let's just construct a bipartite graph with the dominating set in one part and all the vertices, including the dominating vertices here, in the other part, and making a dominating vertex adjacent to all its neighbors in the original graph and itself as well. Now, here is an attack at A and B, and a matching here from the dominators to this attack is a defense, right? Here's another attack at D and E. But this one cannot be defended by AF because there's no matching from AF to DE. Well, this observation helps us to say that the problem is not even in NP. So we build this bipartite graph. Now, given a set D, it's a K-defensive dominating set if and only if every subset of K vertices, so every K attack, can be completely matched to the dominators, to the guards. Well, using Hall's theorem, that means that every subset of the vertex set V of size at most K has at least as many neighbors as itself in this bipartite graph. And in particular, that means that the size of a smallest set violating this condition, called the Hall's violator, has size at least K minus K plus 1. So everything up to K satisfies this. So that means there's no Hall violator of size at most K, which is an NP complete problem. Okay, now this is bad news. For any K, fixed K defensive dominating set is NP complete even in split graphs. And more recently, it has been shown by Henning, Pandey, and Tripathi that it's also NP complete in bipartite graphs. But the K defensive dominating set, if we don't fix K, is sigma P2 complete. Again, a very recent result. Well, what does that mean? I'm not a specialist in theoretical computer science, but informally, let's say, this is the class of problems. This can be seen as second level of polynomial hierarchy class, NP to the MP, which means a class of languages decidable in polynomial time by non-deterministic Turing machines with access to NP oracle, unlike P oracle for NP complete problems. Here, we use an NP oracle, which allows to test the language in NP in a single step. So it is difficult. Okay, so these are two bad news, I would say. So how can we hope to obtain some polynomial cases? First bad news is that given a set D, it is already difficult to decide if it is a feasible K defensive dominating set or not. Even checking the feasibility is not easy. Second bad news, we have exponentially many K attacks, and this fact is independent from the structure of the graph. Even for very simple structures, just take a path on n vertices. You still have n to the K possible K attacks in here, and you still have to counter all these attacks. So how can we hope to obtain polynomial time solvable cases? Well, the question here is, do we really have to consider every single K attack to make sure that they are all countered, defended? The common approach in all the results where we obtained some polynomial time cases is the following. We first show some key result, key lemma, which says that if D defends a few worst attacks, then it can defend any K attack. Of course, here a few means considerably few, right? Fewer. So from exponentially many, we should decrease this number to polynomially many attacks to be checked if we hope to obtain any polynomial solution. And we call those attacks worst attacks in the sense that if we are able, we make sure that we can defend all these worst attacks, then we know any possible K attack can be defended. And here, to obtain such key results, we use the graph structure. Well, this is the list of all polynomial time solvable cases. In the very first paper, 2004, cliques and trees. Well, and then in our first paper, paths, cycles, co-chain graphs and threshold graphs. Here I can say that for cliques, paths, and cycles, we do have some formulas depending on parity, etc. For trees, it's dynamic programming. For co-chain graphs and threshold graphs, we needed some algorithms. And in both cases, we use the neighborhood structure is very, the neighborhoods of the vertices are very structured in these graphs. That's what we use. And the same for proper interval graphs. Then recently, it has been solved for complete bipartite graphs. And okay, this is related to our previous question in the chat. For interval graphs, but not the k-defensive dominating set, but the multi-set version of it. It seems like that makes things a little easier. I just want to give you an idea of how such an algorithm can work. Without going into too many details, I would like to illustrate the idea on proper interval graphs. How do we solve the k-defensive dominating set in polynomial time in proper interval graphs? Okay, for those who know, the proper interval graphs are defined as the intersection graphs of intervals with no containment relation. So no interval contains another one, and they are equivalent to unit interval graphs. So these are intersection graphs of intervals, each one having the same unit length. And it is known that the classical domination is polynomial time solvable in proper interval graphs. So there is hope to obtain more hope, let's say, to obtain polynomial time algorithm for such a graph class. Here is an example of a graph, proper interval graph in the left, and its proper interval representation in the right. So we will use this representation. It will be very helpful. As you see, we number the intervals according to their left endpoints, increasing left endpoints. 1, 2, 3, 4, 5, 6, 7, etc. For proper interval and unit interval graphs, we know that this right endpoint order is the same as the left endpoint order because they are unit or because there is no containment. Now, the key lemma, which is the proof is not that easy, but it's doable, let's say, is the following. D, a set D of vertices defends against every k attack if and only if it defends against every consecutive k attack. And by consecutive, we mean consecutive in the sense of increasing interval ordering. So if I just go back here, for instance, if k is 3, consecutive attacks are the following: 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, and so on. Every 3 consecutive interval forms a 3 attack, right? And this key lemma says that it is enough to consider only those consecutive k attacks. If we guarantee that we can defend them, that it implies that we can defend any other attack. And obviously, the number of consecutive k attacks is just linear, not exponential. Then the idea is just a greedy algorithm, which will consider every consecutive k attack from left to right. So starting from 1, 2, 3, then 2, 3, 4, etc. Well, here I didn't include the initialization. At the very beginning up to k, we need to take a few more vertices. in the set D, but the general idea is that we consider consecutive K attacks, and every time we will add to D, the defenders, the rightmost interval, which is not in the neighborhood. Okay, we look at the neighborhood of the dominators that we have selected so far, right? If it already defends the new K attack, it's okay. If not, I will pick the rightmost element of this K attack, which is not defended, and add it to the defenders. That's it. Simple idea. And we could show that this greedy algorithm finds a K defensive dominating set in a proper interval graph in polynomial time, O of nk. And actually, if you know more about proper interval graphs, they admit a very nice representation called bubble representation, which is a more condensed way of storing the data, let's say. Using this representation, we can improve the running time to n plus b times log k. So b being the maximum bubble size, so at most n, but probably much less. So it's slightly better running time. And here is how it works. Any question from the chat, or you can also just unmute yourself and ask. If there is no question, I'm done with the polynomial time solvable special cases graph classes. And I will proceed with exact solution methods. As far as we know, this is the first exact method. So there is no other exact method for the defensive domination problem in the literature. And we used integer programming formulation, where typically xi's will tell us, so these are binary variables telling us whether a vertex is a defender or not. Then in our problem, we also need to express the feasibility, right? Not only on the neighborhoods, I mean, using the neighborhoods like in the classical domination problem, but for every attack, every K attack, we should be able to find an assignment of the defenders to this attack. And note that a defender can defend different vertices for different attacks. In one K attack, it can defend one vertex. In another K attack, it can be assigned to another vertex. Since we have to make sure that all possible K attacks can be defended. Therefore, we had to introduce a variable yij, saying if I defends j under the attack scenario A, which is 1 if this is the case and 0 otherwise. So we're going to minimize the total number of defenders subject to, well, for every attack, right, one defender, exactly one defender should defend this attack, the vertex j in this attack, for every vertex in the attack. So this is the assignment, matching. But of course, we can only select, we can only say yij a is 1 if the vertex I is selected as a defender. So this is the second constraint, relates the two types of variables, which are both binary variables. Any question for the integer programming model? Okay, I'm sure you can see immediately we will have huge problems here solving this because of this exponentially many attack scenarios here that has to be considered. So the number of constraints is not polynomial, it's exponential. Well, first observation, hopefully we can relax the y variables. Well, taking one of our previous examples, here, if 1, 2, 3, 4 is a defender set, right? So if xi's are fixed, in other words, the problem becomes solving completely independent bipartite matching problems, one for each k attack. So if attack 1 at nodes 0, 1 is defended or not, attack 2 at nodes 0, 2, and so on. Here in the right side, we have all possible k attacks, 2 attacks here. In this case, k is 2. And we need to find a matching from the defenders to these attacks. And these problems can be seen as independent bipartite matching problems, which we know can be solved by, relaxing the y variables here. And we can actually relax y variables and obtain an optimal solution to this integer programming model. But as you may guess, the size of the instances we can solve with this model remains very limited. For k equals 2, it's less than 100. And for k equals 3, it's less than 50 if we give 10 minutes. So we need to improve the performance of this model. And here the idea is the following. We're going to decompose the problem using Bender's decomposition into one master problem, which contains the complicated variables, which are x's. So here, by complicated, I mean binary. And the subproblem containing only the relaxed continuous variables, y's. The master problem minimizes the number of selected vertices, dominators, subject to, so this set of selected vertices should be a feasible defender set. But at the beginning, we have nothing, no constraint at all of this type. This is the task that we feed to the subproblem. For a given a set X found by the master problem that we call X hat, it's an input for the subproblem. The task of the subproblem is to decide if it is a feasible defender set, and if not, finding a constraint which is violated, which has to be added, therefore, to the master problem, and we're gonna loop this way. So the idea in Bender's decomposition is that we solve the master problem, which consists of the x variables. It provides a solution x hat, which is fed into the subproblem. And the subproblem decides if x hat is a feasible solution or not. If it is feasible, then the solution provided by the master problem is optimal because we started with just no solution, no constraint at all. So it minimizes the number of vertices under no constraint, right? And the constraints are added as needed. If the subproblem is infeasible, then we're going to use the dual of the subproblem, which is unbounded, and generate a feasibility cut obtained from the extreme rates of this dual of the subproblem, which looks like something like this, where alpha hats and beta hats are the optimal solutions of the dual of the subproblem. So this is typically the feasibility cut added to the master problem, which is solved again, which returns a new defender set sent to the subproblem again, and so on until the subproblem finds a feasible solution, which is therefore optimal. Well, there are a few implementation details. I'm not going to show the runs for that, but we made several experiments and decided to run the algorithm with, as we call it, the callback function. So here, instead of the traditional manner of adding, solving the master problem to optimality at each iteration, we use a branch and Bender's cut scheme where the callback function is integrated into the MIP solver. Here, the feasibility cuts are generated in a dynamic way during the branch and bound process whenever they are needed. It turns out that this is a more efficient implementation. So this is the one we adopted. And also, in Bender's decomposition, the classical approach is to add one aggregate feasibility cut, which takes into account all k attacks obtained from the extreme rays of the dual of the subproblem. So it takes into account all k attacks which cannot be defended by the current set of defenders, and provides one aggregate feasibility cut as the one I have shown here, this one. Well, instead of this, we found it more performant to decompose the subproblem and find the worst whole violator using either linear programming or some combinatorial methods. So all we need to find is an attack which is not defended. And if there are many, we can search for an attack which violates more this whole condition, so that the cut is deeper. So this is typically the cut that we add in this one cut approach, and it turns out that it is more efficient. Okay, with these implementation details, we also added two heuristics. The first one, to generate a set of initial cuts or attacks. Instead of starting the master problem, solving the first master problem with no constraint at all, we generate an initial set of attacks that we hope they are bad attacks, hard to defend, before the subproblem generates Bender's feasibility cuts. Well, for this, we had the following idea. We compute closed neighborhoods of the vertices and build inclusion chains like this. Of course, there are many inclusion chains. We build maximal inclusion chains, and the intuition says that bad attacks will occur at vertices which are at the beginning of this chain. Because they have small neighborhoods, it will be harder to defend them, to find a matching to them. So we take some of these, as we call it, minimal vertices to form k attacks and add them at the initial master problem. Again, using experiments, we decided to add in practice 0.5% of the total number of attacks as initial cuts. After some trials, we found that this is it's good trade-off. And the second heuristic that we call a warm start is to find an initial set of defenders. So if we solve the master problem the first time with no feasibility cut, no attack at all, the first set which is returned as defenders will be obviously an empty set. Minimize sum of xi's under no restriction at all, no attack, so just 0, right? Instead of this, we identify a first solution as an initial set of defenders and fix them to 1. So these guys are defenders. Again, we use the closed neighborhoods to this end. But this time, and we build these inclusion chains of the closed neighborhoods, But this time, vertices with larger neighborhoods, bigger neighborhoods, are better choice for defenders. So we pick some of these maximal vertices, at least k, since any feasible defender set will contain at least k vertices, and add them, feed them as a warm start defenders to the master problem. Well, two things can occur here. First, if D is not feasible, then we proceed with Bender's feasibility cuts, right? If, in contrast, we added too many vertices, D is feasible but not optimal, then it will simply provide us an upper bound on the optimal value. And in practice, yes, we started with 2k initial defenders in our computational experiments. Now, any question for the methodology? Otherwise, I will proceed with some experimental results. So here, we tested our algorithms on Erdős-Renyi, randomly generated Erdős-Renyi graphs, the classical test bed, but also we make experiments on chordal graphs. Note that the problem is NP complete when for fixed k already in split graphs. That's what we have shown at the beginning of this talk. And split graphs are chordal, so it's also hard in chordal graphs. And here we used chordal graph data sets from one of my previous works with some colleagues and students about generation of random chordal graphs. I just wanted to mention this link and the GitHub link as well, because I know that many domination problems, but also many other hard problems remain NP hard in chordal graphs. And if you have methods, heuristics, or any other kinds of algorithms that you would like to check on chordal graphs, you do have, so you have access to this open source generator. You can find some data set of chordal graphs, but you can also generate your own graphs of different densities and sizes. Yes, we took averages over 5 instances for each combination of order and density. And this is our programming platform properties. And here are the first results. Well, this is for Erdős-Renyi graphs for k equals 2. The first set of columns, one-cut benders, is the standard method that I introduced with the implementation details, one cut instead of aggregate cut, and callback mechanism. Then we added heuristic 1 to this version, or heuristic 2 to one-cut benders, or both heuristics combined in the last column. Well, maybe before talking about this, the results here, I would like to remind you that for the classical domination, which is much easier than the K defensive domination is much harder, I can say, than the classical domination. And the classical domination can be solved in an exact way to optimality using the state-of-the-art methods up to around 100 vertices in reasonable time. So it's a very rough rule of thumb. 100, 150 maybe. And here, for k equals 2 Erdős-Renyi graphs, we could go up to 150, but not being able to solve all instances. So our time limit is 10 minutes. But we can observe here that, so in red, the combined version, or the heuristic one, the purple here, is better than the original one-cut version, slightly better. And in the right chart here, you can see the improvement over the one-cut when we used only heuristic 1, only heuristic 2, or in green combined. So for different densities, 0.2, 0.5, 0.8. Likewise, for k equals 3 in Erdős-Rényi graphs, the combined version provides some improvement. So the conclusion for Erdős-Rényi graphs is that heuristics provide a slight improvement. So there is still room for more improvements here. And we can solve the k-defensive dominating set with at most 150 vertices for k equals 2 and at most 100 vertices for k equals 3 in a given, where the given time is 10 minutes. After that, we stop. Well, when we look at similar results for chordal graphs, we see that we can go much further. The size here go up to 500, but actually, as I said, it's an ongoing work. We say time limit 10 minutes here, but actually we can go much further in 10 minutes. Here, the runs stopped in 1 minute. So we could find the optimal for all instances in 1 minute, roughly, at most. And here we can see that heuristics provide a better improvement on the one-cut Bender's version. Okay, this is my timing, but 45 minutes only. I'm about to conclude. Yes, for k equals 2 and different densities, we can see that the red line here represented the combined, two heuristics combined, performs much better than the one-cut Benders. The same thing where we combined different densities. So before it was for each density 0, 1, 0, 5, 0, 8 separately. If we combine all of them, we have a clear improvement when we use the combined heuristics, two heuristics together for chordal graphs. So the conclusion here, maybe also for k equals 3, here we could go up to 200 vertices in, again, the same limit of 10 minutes. And again, the combined version is better. So the conclusion for chordal graphs is that the two heuristics combined together perform consistently better than one-cut Benders on chordal graphs. And this improvement is more pronounced for chordal graphs than for Erdős-Rényi graphs. And actually, this was, we were expecting this because of the way we constructed the heuristics based on the neighborhood containments. And we know that chordal graphs have very nice structure for this on their the neighborhoods of the vertices. And to summarize, we can solve k-defensive domination for chordal graphs with up to 500 vertices for k equals 2 in 1 minute, and up to 200 vertices for k equals 3 in 10 minutes. For low densities, I think for all here, I should have removed for low densities. Okay, so here's my conclusion. Of course, we need to make more experiments, in particular for higher k as well, and improve the performance on Erdős-Rényi graphs, maybe better heuristics. Here, note that the main difficulty with the heuristics is that we do not have, so far, a heuristic which guarantees a feasible defensive dominating set. Checking the feasibility is a hard problem, right? I mean, of course, if we take all vertices, it's a feasible defensive dominating set. But apart this trivial and very bad feasible solution, we don't know how to construct a feasible one. Maybe we can try to derive some valid inequalities for special graph classes like Chordal or others. And for the exact methods, we can say that we can already see that it has its limits as long as we consider these variables based on every attack scenario. And a remedy for this can be using bi-level optimization ideas. That's it. Thank you very much for your attention. Ready for your questions if you have some.
Tınaz, thank you so much for your nice presentation. Any questions? We would be happy to listen your questions. If you have any question, please turn on your mic and ask your questions. Okay, please ask your questions.
Where is it possible to find the lemmas, the interval graph lemma proof?
Yes, I saw this in the chat now. Maybe I can share again the screen and show you the related reference here. Interval graph, it's this paper. So discrete applied math. And you mean that one, right? For proper interval graphs. If we can defend every consecutive attack, then we can defend all of them. Is it the one you are asking?
Yes, thank you very much.
Yeah, that one. The defensive domination problem in proper interval graphs.
Other questions? Okay, James, please ask your question.
Hi, thank you for the talk. I wondered what difference it would make if you made the additional requirement that once your guards at the dominating set have reacted to the attack, that the resulting set is still a dominating set. So it's more like eternal domination.
Yes, yes. This is definitely one of the versions that we are considering. But so there is, in emergency response problems, practical problems, this is indeed an issue, right? You want your set to remain a dominating set after answering to the attack. And this, so there is, if you require this for only the next step, then we talk about secure dominating sets. If you want it to hold for eternally, then it's eternal dominating sets. So one thing that we have in mind as future work is also considering the defensive versions of eternal or secure dominating sets. So we have k simultaneous attacks, we answer these attacks, and we want the new set after the movement, right, to remain a k defensive dominating set. This is indeed a nice direction, but for sure it will not be easy.
Okay, thank you very much.
Thanks for the question.
Okay, other questions? Okay, Tınaz, I have one question.
Sure.
Have you been studied other types of defensive dominating set? I mean, for example, total defensive problem connecting.
No. No. Well, as you see, it was from the very beginning, it was really hard to obtain any polynomial cases. Already for paths, cycles, complete bipartite graphs, it wasn't trivial. And then came this cochain threshold and proper interval graphs, thanks to their nice neighborhood structures. But any further graph class will be much harder. So it's my intuition. Then if you consider further versions, they are indeed very interesting, both theoretically and from practical point of view, and wide open. Yeah, but
Okay, thanks for your information. Other questions? Okay, let us thank speaker again. Tınaz, we hope to meet you someday in Novosibirsk in the future.
yes.
Well, actually, we are planning to organize an international conference next year in August. But as I know, you said me you will be busy that time. Yes.
Yes, it will be hard for me to make it in August, right? I'll think it twice, but not sure I'm gonna be able to do that.
Anyway, we are looking forward to meeting you in Novosibirsk someday.
Me too.
Yeah.
I would really like to visit Novosibirsk once.
Okay. Thanks.